at implicit differentiation. So we have been doing derivatives over and over and over again. But you'll notice like all of the equations we have been doing the derivative of are set up the same. They're all y equals something. But does an equation have to be y equals before we can do anything? No, we know from like graphing calculator, if you want to plug something in and get a graph, it has to be y equals, but there are situations where we might have x squared plus y squared equals 6. And that's not set up where we could just plug it into the graphing calculator. So how could we approach those types of problems if we needed to find the derivative? So that's all I'm saying. Here we're used to what's called an explicit function where it's y equals, but it might be implicit where the y is somewhere else within the equation. So let's say I gave you something like this. All right, let's practice first. Let's just solve for y. So we know if I wanted to do the derivative like I have been, I would have to get it to be y equals. What would I do? Okay, you can either add the y squared over or subtract the x and then divide by -1. And then what do you do? And if you had a square root? So we get y equals plus and minus the square root of x. Okay. We haven't really done a derivative where we had a plus and minus, but do you think you could? Probably. What would we probably just have on our derivative? The plus and minus would really just trail down. Okay. What if I gave you this one? Can you solve for y? Yeah, subtracted the x squared, square root. Can you do the square root of the 100 and the x squared separately? No, because it's more than one term. Just like if I gave you x plus 10 squared, you can't just say that's x squared plus 100. You would have to FOIL. So same principle, when we have that square root, we can't do each piece, so it's just plus and minus square root of 100 minus x squared. Okay, so both of these wouldn't be too bad to do a derivative because we could solve for y. And we have that option. We could get the y by itself and then do our derivative like we have been. However, that's not always the case. If I gave you x cubed plus y cubed equals 3xy, could you get that to be y equals something with no other y's in that equation? Probably not. So this one, I can't solve for y. It's impossible. But I still need to be able to do the derivative. To do that, we are going to do all of our derivative rules like normal and do our derivative in terms of x. And then at the end, we will solve for dy dx. Okay, what I mean by that is if I gave you the equation like y equals 4x cubed. We know when we do the derivative of y, we can call it y prime. We can also call it dy dx. We've seen that notation. And so if I did the derivative 4x cubed, that gets a 12x squared. So that's like what we have been doing. If I gave you x equals 4y cubed, and I wanted the derivative with respect to x, that means when I do a derivative of x, it's like normal. So the derivative of x is just 1. We do our derivative of y the same way, so that would be 12y squared. But then we have to do the extra piece. Because we're doing our derivative with respect to x, any other variable has to get a notation with it. it would have a dy dx with it. It's kind of like the chain rule. The derivative of y is dy dx. So every time we do a derivative of a y, we will throw a dy dx on it. And then at the end, you could solve for that. We could divide, so we could say 1 over 12y squared is equal to dy dx. And we still got our derivative without first solving for y. So that's the technique we're going to use. It's called implicit differentiation. So basically, instead of trying to solve and get the equation y equals in the beginning, we do all of our derivative rules like normal. We just treat y as another variable, but every time we do the derivative of a y, we write dy dx beside it. So let's look at one. All right, let's do implicit differentiation to find the derivative of x squared plus y squared equals 100. So derivative of x squared plus derivative of y squared, 2y, but we did the derivative of a y. So beside that, we write dy dx, just like the chain rule, derivative of y is dy dx, equals, what is the derivative of 100? 0. So now we could solve for dy dx. Go from 2x divided by 2y. So derivative of y is negative x over y. Second part of this equation, I asked for the slope of the tangent line at the point 6, 8. Not a full equation, just the slope, so what do we do? Slope of a tangent line is just our derivative. So x is 6, y is 8, and we get negative 3/4. And we could write the full equation of the tangent line if I asked, but it's still a derivative, so it's still representing the slope of that tangent line. Questions there? So we're just practicing this all day today. So if I ask for the slope of a line tangent to x cubed plus y cubed equals 3xy. Slope of a tangent line. So what do we need? We need our dy dx. Okay. So anytime I see that slope of a tangent line, that's my dy dx. So we have to do the derivative. So derivative of x cubed derivative of y cubed. Equals. Over here, x and y are each a variable. So to do that derivative, we have to do the product rule. So product rule says derivative of the first. So derivative of 3x is 3. Second one stays the same. Plus the first times the derivative of the second. The derivative of y, 1 dy dx. Okay. Let's take a look now. I need to be able to solve for dy dx. The original problem, there is no way I could have gotten that 3y equals. But we can get dy dx by itself now. Let's move all the dy dx's on one side and everything without it on the other. So 3y squared dy dx, going to subtract over the 3x dy dx equals 3y minus 3x squared. Subtract over dy dx. Now what would we do? Divide it. Yeah, it's multiply with the dy dx, so we can divide it over. Is there anything we can do to reduce? What do all these terms have in them? Okay, so let's just divide everything by 3. So we get y minus x squared over y squared minus x. So that is my derivative. We had a little more work to do at the end to solve for dy dx, but it was a lot easier to do that versus trying to solve for y before we did the derivative. Then I asked for the equation of the tangent line. So we know we need a point and a slope. My point was 3 halves, 3 halves. So 3 halves squared. I plug that in to my derivative, I would get my slope, which is -1. And y equals mx plus b. And we have the equation of the tangent line. Is this okay? I do want to mention one thing in this problem. We'll make sure everyone has it down before I erase anything. If I don't actually ask you for the derivative, so if I never actually ask you to give me this, if I just said, tell me the slope, you have the option of plugging in your x and y before you solve for dy dx. And that can sometimes be easier for people. It's the same thing, so if I don't ask you to write out the whole derivative, you could at this point say, you know what, I think it's going to be easier if I go ahead and plug in my points. And then you would have numbers and you could solve for dy dx there. You guys know what I'm saying. So if I only ask for the slope, you can plug in x and y either before or after you solve for dy dx. But if I ask for the derivative, you have to get the dy dx by itself. Let's try another one. So if I ask for the equation of the line tangent to sine of x plus 2y equals 2x cosine y at the origin. So equation of a tangent line, y equals mx plus b. I need a point and a slope. What's my point? my slope is the dy dx, so we have to do our derivative. All right, everybody's favorites here. So let's think about it. This is sine of that. So chain rule says derivative of the outside. So derivative of sine is cosine. Inside stays the same. Times derivative of the inside. So what is the derivative of x? What is the derivative of 2y? Equals. On this side, we have a 2x that has a variable and a cosine y that has a variable. So since they each have a variable, we have to do product rule. Derivative of the first. Derivative of 2x is 2 times the second plus the first derivative of the second. What is the derivative of cosine? Inside stays the same. But we did the derivative of a y, so times derivative of the inside. Derivative of y is okay, this is an example. Did I ever ask you to tell me what dy dx equaled? No. So you could solve for it, or if we wanted, we could go ahead and plug in 0, 0 first, and that would probably be a lot easier here. So if I put that in, cosine of 0 plus 0. So cosine of 0 is 1 times 1 plus 2 dy dx equals 2 times cosine of 0 is 1 plus 2 times 0, so this whole term just drops off. So if I want to get dy dx by itself, we can subtract our 1, divide by 2. This doesn't mean that my derivative is always 1/2. It means at the point when we're at 0, 0, the derivative is 1/2. So this is our slope. Again, the y equals mx plus b. So we get a y-intercept of 0. So the equation of the tangent line is 1/2 x. I want you guys to try a problem. What questions do you have for me on this one? So really, it's the same thing, but every time you do a derivative with a y, you have to write dy dx with it. And that's the only change. Why don't you guys try example 5? So you could, this is one where you could solve for y first, but I don't know that it's actually going to make things easier, because you'll end up with a square root and you'll have to do the chain rule within that, and so it's not necessarily saving us time, just a way of rewriting it. So if we wanted to jump right in with the derivative, derivative of x squared would be 2x. Derivative of y squared would be 2y, but it's like the chain rule, so times the derivative of y, which is dy dx, equals, what's the derivative of 25? 0, because it's a constant. So subtract over 2x, divide by 2y. So dy dx is negative x over y. Then I want the equation of the tangent line at the point 3, 4. So our slope is just dy dx if we plug in the x and y. So we get negative 3/4 4 from x plus b. So y equals negative 3/4 x plus 25/4 for the equation. Is that okay? Let's do a couple more. So if I ask for y prime, what does y prime mean? Derivative, same as dy dx. I strongly advise you to not write y primes in your problem, just because when you start looking at it and you have things like 3x to the 4th plus 5y squared y prime plus something else, it starts getting really confusing that y prime can lose its prime very easily. So I would stick with dy dx. It's a lot easier to recognize that. So derivative of x cubed plus derivative of y cubed. Okay. Now 6xy. Notice it has two variables. So what do we have to do? Product. We have to think of it as a 6x times a y. So derivative of the first, derivative of 6x is 6 times the second plus the first derivative of the second. Derivative of y would be dy dx. Alright, so let's put all the dy dx's on one side and everything without on the other. We take out the dy dx. Divide. I do want you to simplify as much as possible. We really have 4 pieces. What can they all be divided by? 3. So we have 2y minus x squared over y squared plus 2 minus 2x. I think I'm going to stop here for today and let you guys try some, and then tomorrow we will do more examples. We are, for the first time in a long time, going to use our books. On this, we could go up through 36, but that's not going to be due tomorrow. So this is kind of the assignment for today and tomorrow, so that little chunk you should have done, what is it, Wednesday? So Friday.